This is the first of two videos that is going to illustrate how we can represent the electronic character, electronic makeup of an atom. And so we do this in two ways. One is with what are known as energy level diagrams, and one is with what are known as electron configurations. So I'm going to show you energy level diagrams today. First of all, though, we do have to talk about the rules of filling. But just to quickly show you this, if this is an electron, if sufficient energy is added, as we've talked about before, as we've seen before, the electron gets promoted, and so it gets promoted to a higher energy state. And so in the lower energy state, we talk about the electron being in the ground state. And when it gets promoted, it's in an energetically higher state, and it will eventually de-excite to go back down to ground state. But this is really what we mean by the energetics. And so when we look at energy level diagrams, we look at something like this. This is one representation over here on the right, and it just lays out for us the different energy levels. Remember, the principal quantum number n tells us something about the energy levels. So it shows the different energy levels increasing as the arrow suggests, and then has the different subshells. And as you'll see, we can break those subshells down even further into orbitals. So this is really what we're going to end up generating, but broken down further still into orbitals. So let's get started with the rules of filling. So the first general guideline or rule is stated as the Pauli exclusion principle, which says that only two electrons with opposite spin can occupy the same atomic orbital. Now, we saw this previously, as no two electrons can have the same set of 4 quantum numbers. So this is just a different way of saying the same thing. So let's kind of see how this works. So again, you can see here's my energy, increasing energy from bottom to top. I'm going to put these 3 electrons into 2 different s orbitals. And so I'm going to start at the bottom, and I'm going to put an electron in. And so I'm also going to show a representation of electrons. So that half arrow is an electron. And this is said to be upspin. Remember, I mentioned before, electrons have 2 spins, up and down. So that down pointing half arrow is an electron with down spin. And so that's how we're always going to show them. So first electron I've put in is upspin. I can put 2 electrons in the same orbital. That's according to the Pauli exclusion principle. So I'm going to put one in, but it has to have opposite spin, again according to the Pauli exclusion principle. Well, I still have a 3rd electron. This orbital is full, so I can't put an electron there. So I'm going to go to the next orbital. And there it is, another 3rd electron. So 2 electrons per orbital. If there are 2 in the same orbital, they have to have opposite spins. Next guideline, Hund's rule. Electrons prefer parallel spin in separate orbitals, subshells. So separate orbitals of a subshell. So another way of saying that is electrons half fill a subshell before they pair up. And when they do pair up, again, they have opposite spins according to the Pauli exclusion principle. So let's look at how Hund's rule is applied. I'm going to put 4 electrons into this p subshell. Remember, a p subshell has 3 different orbitals. So I'm going to put 4 electrons in there. So I put one in. There's an electron with upspin. Now, Hund's rule says we half fill the subshell. So I can't put one in this first one. I'm going to put one in the second one. And I put it in the second orbital with the same spin. Parallel spins, they're both upspin. I keep going. I can't put one in the first or the second, so I put it in the third with the parallel spin. Now I've half filled the subshell. I have to pair up now, and when I pair up, it's with opposite spins. So there's the 4 electrons in a p subshell in the 3 different orbitals of the p subshell. That's Hund's rule. Finally, we have what's known as Aufbau principle. And Aufbau principle is maybe the simplest one, and it's kind of where we start in a way, but electrons are placed in the lowest energetically available subshell. And so in showing you this, I'm basically showing you how to do an electron configuration. So Aufbau says we start at the bottom. We start at the lowest energetically stable subshell. Well, again, here's my energy guideline. Increasing energy from bottom to top. I'm going to put 6 electrons into these orbitals. So Aufbau says they start at the bottom. So there I start at the bottom with that first lowest energy subshell. And I can put 2 electrons in there. But now that's full. Pauli exclusion principle. So I'm going to go to the next energetically available subshell or orbital. It's another s orbital. And so I fill that. And so I've now filled that second s orbital. Next energetically available orbital or subshell is this p subshell. I have 2 electrons to go. 1, and according to Hund's rule, I half fill. So there's the second. And I'm done. There's 6 electrons in there. Aufbau, starting at the bottom. Pauli exclusion principle, 2 electrons per orbital. And Hund's rule, I half fill the subshell before I fill it. So this is pretty straightforward once you get the hang of it. And so we're just going to do a few examples. So let's first of all look at fluorine. So if you remember from the atomic notation, that's the atomic number, which indicates number of protons and, by extension, in a neutral atom, the number of electrons. So in our energy level diagram, we want to get out 9 electrons. So Aufbau, start at the bottom. 1, 2. 2 electrons with opposite spins in the same orbital. Aufbau, next available energy level, 2 electrons. Hund's rule, into the p block with 3 different orbitals, so I half fill first. And now I've just put out 7 electrons. Now I have to start filling the p orbitals. And there's my 9 electrons. So that would be an energy level diagram for fluorine. Not that tricky. Argon, 18 electrons. Here we go, 18. And so we're going to start at the bottom. 2, 4, 7, 10. And notice here, this is, I just want to pause for a second here and look at what we have here is a filled energy level. And that is a very stable configuration. And so, not surprisingly, we're representing a noble gas here. If I was to stop here, I would have done an electron configuration for neon. So neon has 10 electrons, 8 of them in the second energy level, which is a filled energy level. I mean, in fact, helium, which is also a noble gas, has a filled energy level, the first energy level, n equals 1. But we're not doing these two, we're doing argon, and so we're going to keep going. We have 8 electrons to go. So there's 2, and then Hund's rule. And now I'm done. And so argon also has a filled energy level. So argon is also a very stable configuration. So you hopefully kind of realize why the noble gases are not reactive by looking at this. Their energy requirements are taken care of pretty well. We have a filled energy level, which is very stable. Let's do one more. Germanium with 32 electrons. And so I'm just going to start putting them in. So we go through neon, that's neon. We get up to argon, there's argon. And I just want to pause for a second here and point out, if you remember I showed in a previous video, the 4s is actually energetically below the 3d, and you should be able to see that with this faint dotted red line. So 4s below 3d. So this is why we fill 4s before 3d. So I have 18 so far, so that's 20. And I'm going to put 10 more in. That's 30, and then I'm into the 4p subshell. 4p is below 5s, so according to the Aufbau, we fill it first, and so it half fill. And so there is the electron or energy level diagram for germanium. Now, Like all things in chemistry, there are some exceptions, and so I do want to point out two exceptions. So the first exception is chromium, in which we would see that there's 23 electrons, and so, or 24 electrons, and so I need to put those in my energy level diagram. So I'm going to start building up. That's what Aufbau means, building up. And so I start at the bottom. There's neon. And here comes argon. And now 2 in the 4s, and that leaves 4 electrons to go. That's 20 electrons, so I'm going to put my 4 electrons in. And so we would predict that would be the electron configuration for chromium. And according to Aufbau and according to, we've followed all the guidelines, we filled up from the bottom up. 4s fills before we add to 3D, but this is an exception, and so what happens in this exception is one of these electrons actually gets promoted to there. And so instead of having 2 electrons in the 4s, I only have 1. And then I have this 5th electron in the 3D, and so what that creates is a half-filled subshell. And a half-filled subshell is stable. More stable than having 2 electrons in the 4s and only 4 electrons in the 3D. So that is an exception. And so you just need to remember that exception. Now there's going to be another exception, much like the exception for chromium, and that does actually exist. And where do you think that's going to lie? Well, what element would have essentially the same valence shell configuration as chromium? And that element is going to be the element directly below chromium on the periodic table, and that's molybdenum. So here's molybdenum, and so I've already got it going, and so that's argon, molybdenum. We fill the 3D block now because it has more electrons. And we fill the 4p, and now we're into the range where the exception occurs. And so we would predict 2 electrons in the 5s, but there's only 1, and then we half fill the entire D subshell. And so there's the 42 electrons that make up the electronic configuration of molybdenum, and that's an exception to the guidelines we followed. So 2 exceptions based on this type of difference. Chromium and molybdenum show the same type of exception. Well, there's another exception. So copper is the exception I want to draw your attention to here. And so copper, we would predict this to be the electron configuration for copper. I've only shown the 4s and 3d, so I've shown the last 11 electrons that go in to make copper. And again, we would predict filling the 4s and then adding electrons until we've run out of them to be housed in the 3D subshell. And so that's what it would look like. Well, not surprisingly, this exception is similar in that we only have a single electron in a 4s, and then we're going to fill the 3D subshell. So instead of having 9 electrons where there could be 10, we fill it. And so again, what we have now is this exception of a filled subshell. And so a filled subshell, again, is stable. Oops. Do that in the right order. And it's, again, more stable than the predicted configuration that has 9 electrons in the 3D subshell. So copper is an exception. So what is another exception? Well, directly below copper, we find silver. So once again, silver will have exception to the predicted energy level diagram, where we have 10 electrons in the 3D subshell instead of 9, and only a single electron in the 5s subshell. And so that concludes this video. Just to quickly wrap up, we talked about the Aufbau principle, which is building up from low energy up to high energy. So we go up in order. We talked about Hund's rule, which is we half fill before filling. And that's when we talk about, really you only have to worry about that in subshells where there's multiple orbitals. So the P, D, F, anything above that. The S, I guess we do half fill it, but we half fill it, then we immediately fill it. And then we talk about the Pauli exclusion principle, 2 electrons per orbital with opposite spins. And so those are the 3 guidelines we looked at for preparing or generating our energy level diagram. And this is what an energy level diagram looks like. That was our one for argon. And that concludes this video.